Good morning.
Good morning, sir.
Shall we start?
Yes, sir.
Okay. In the previous class, we have discussed about uh, stress distribution for stress transformation for biaxial stress condition. This was the biaxial stress condition. Biaxial essence along two axes there was normal stresses. Only there was normal stresses. There was no shear stress induced. In this today's class, we'll discuss simple shear state. There is only pure shear. There is no normal stresses. When there is a state of simple shear, pure shear, there are no normal stresses. There is sigma x or sigma y or sigma z is zero. Only it is subjected to pure shear. Okay, discuss that. Stress transformation for pure shear. Stresses induced by state of simple shear or pure shear. There are no other stresses, only shear stresses are induced, and hence the name simple shear or pure shear. As usual, this is nothing but the body in which I am taking a point. This is the point I am taking. This is a region which I am focusing. If I take that region, if I take a plane in that region, we subject it to one simple shear. For example, let us assume the stress state at that point be like this. Stress state at that point be like this. Normal to the plane is x, stress is acting in the y direction. As soon as you write tau xy in this direction, opposite face you should write an arrow in the downward direction, and then these two arrows should meet. This is normal to the plane is tau yx, and then these two arrows should meet. This is how we should represent. This and this is causing anti-clockwise anti-clockwise movement. This and this is causing clockwise movement. So total movement is equal to zero. Summation of force is equal to zero. Okay. Now I can write up, since due to complementary shear stress, tau xy is equal to tau yx. Instead of that, I will write in just tau. It is nothing but tau only. Okay. Now let us go ahead and solve this. If I take, okay, I'll go to the next slide. If I take and represent here only, let this, I will call it as A, I will call this as, this is also green, I will call this as A, B, C, D, okay, and let this point be E. I'm measuring anti-clockwise, top down with the clock towards the hypotenuse. This is my angle theta, which is in anti-clockwise sense, and then this is positive. As soon as I take this, I'll take an element BCE. I'll take the element BCE. Take the element BCE. I'm interested on stress transformation for the plane BE. I've taken an element BCE. Stress transformation in the sense I'm interested in normal and tangential stress on plane BE is subjected to tau. Okay. Now I have to take for equilibrium. For equilibrium, there should be a normal stress acting sigma n like this, and tangential stress sigma t acting like this along the length like this. Okay, this is my normal direction. This is my tangential direction. Okay, now I will express my write it here. Write it here. I'll write uh, instead before that, instead of stresses, I'll be representing it as forces. The procedure remains the same for all the stress states. I will call this as force acting downwards. First, I will call this as whatever you want to call, F1 or F2 you can call, irrespective of it is your convenience. F1, F2. I will call this as Fn. I will call this as Ft. Okay, this is phase B, C, E. Okay, F1 sigma is equal to F by A, or sigma into A is equal to F. Therefore, F1 is equal to sigma here is nothing but tau. You can call tau xy if you want, or you can just write that is called tau xy. If you want to call tau xy, let me call tau xy only. Tau xy and tau yx are on the same. For convenience, I'll be calling this tau xy for understanding. Tau xy, F1 is equal to tau xy. This is tau xy into CE into 1. F2 is equal to, that is also tau xy into BC into 1, BC into 1, because this area is this is of thickness, length BC and thickness 1 unit. Similarly, length CE, thickness 1 unit. Similarly, F of n, which is equal to sigma n into face BE into 1, F of t, sigma t, this is nothing but tangential stress, BE into 1. Okay. Next, I should write the equilibrium equations. I'll write it. Okay, I'll resolve it. Resolve it here. For resolving, first I will draw the xy plane. With reference to xy plane, at what angle my new plane is there? We'll see xy plane. This is at an angle theta. If this is theta, I've already discussed. This is theta. This is theta. This will be also at an angle theta. We have discussed that. If you take a vertical, this will be also at an angle theta, and therefore this will be also at an angle theta. Okay. Therefore, with reference to my xy coordinate system, my normal axis is at an angle theta. My normal axis, n axis, is at an angle theta. I'll represent that n at an angle theta. Perpendicular to it will be tangential axis t. Okay, along the normal axis, if you want, if you are not confused, you can write along the normal axis. I have my f of n acting. Along tangential, there is sigma n acting, and sigma t, it is nothing but f of n, f of t. Okay. Now, now, uh, now, force. If you can see here, f of 1 is acting in this direction. Right, f of 1, perpendicular to it. Draw this length parallel to this. Give me a moment. I'll come back. Give me a moment. sorry. Okay, this is x-axis. Okay, x, x normal at an angle theta along x-axis. There is force F1 acting in this direction. You can see here force F1 acting in this direction. I'll represent this as F1. Okay, and if I resolve this force F1, I'll draw a perpendicular. This is my perpendicular. Okay, this is F1 theta. Opposite will be F1 sin theta, F1 cos theta. This is the resultant force F1. Arrow should be like this. Okay, this is about F1. There is also force F2 which I want to resolve in the normal and tangential direction. Let us go to force F2. Let me write the plane XY. X, Y, normal, tangential. My plane, what is there? B is at an angle theta from the XY coordinate system. That is what this indicates. Okay. Now, if I want to resolve this force, this is Y. This is my perpendicular. My force F2 is acting downwards. F2. If this is theta, this is 90 degree to each other. If this is theta, this will be 90 minus theta. This will be 90 minus theta. So that this and this will be add together and become 90. This is 90 minus theta. This will be theta. Okay, F2 acting downwards. This is theta. Arrow should be. This is the resultant. Arrow should be like this. Don't do mistakes by taking the arrows directions. F2 sin theta. F2 cos theta. Right? Resolve the force. Only thing the difference in the previous case, the normal stress and the shear stress was in the case of normal stress, this force F1 was acting in the positive extension. It was acting like this. See, we will see what is the difference of this force, this shear stress acting in towards left hand side. Okay, we see there's a lot of difference. Okay, now, according to for equilibrium, summation of forces in normal direction should be equal to 0. Normal direction, there is force F of n. If I resolve it, there is a force F of n minus F of 1 cos theta is acting opposite to the normal direction minus F of 1 cos theta. And this F of 2 sin theta is also acting opposite to the normal direction minus F of 2 sin theta is equal to 0. Summation of forces in tangential direction should be equal to 0. There's a tangential acting along the t-axis, F of t positive, okay, plus F of 1 sin theta acting along the tangential axis plus F of 1 sin theta minus F2 cos theta is equal to 0. Minus F2 cos theta is equal to 0. We have resolved this. Okay, we'll go ahead and solve this. I can write this as 1, this as 2. From 1, F of n is equal to F of 1 cos theta plus F of 2 sin theta. F of n is equal to sigma n into b, sigma n into b is equal to f of 1 is equal to tau xy into c, tau xy into c cos theta plus f of 2 f of 2 is equal to tau xy into bc, tau xy into bc sin theta, or I will divide 2 out by b in order to get the normal stress. Sigma n is equal to tau xy c by b cos theta plus tau xy bc by b sin theta. I'll write it here. Therefore, sigma n is equal to tau xy c by b, c by b, this is theta, or you can see here c by b, which is nothing but sin theta, opposite by c by opposite by hypotenuse, c by b is sin theta cos theta plus tau xy bc by b, bc by b is cos theta, tau xy cos theta sin theta. Okay, or I can write therefore sigma n, which is equal to 2 tau xy sin theta cos theta, or sigma n is equal to sin 2a is equal to 2 sin a cos a sin 2 theta by 2, or sigma n is equal to tau xy sin 2 theta. This I will call it as 3. Sigma n is equal to tau xy. This is the expression for sigma n. Now let us go ahead and find the expression for f of t, tangential stress. f of t is given by f of 1 sin theta minus f of 2 cos theta. f of t from 2 f of t plus f of 1 sin theta plus f of 1 sin theta minus f of 2 cos theta is equal to 0, or f of t which is equal to minus f1 sin theta plus f2 cos theta. f of t is given by sigma t into b, sigma t into b is equal to minus f of 1 is given by tau xy c minus tau xy c sin theta plus f of 2 tau xy bc cos theta. If I divide throughout by b, I'll get sigma t, which is equal to minus tau xy c by b sin theta plus tau xy bc by b cos theta. Therefore, sigma t, which is equal to minus tau xy c by b is sin theta minus tau xy sin square theta plus tau xy bc by b is cos theta is cos square theta. Therefore, sigma t, which is equal to tau xy cos square theta minus sin square theta is cos 2 theta, cos square theta minus sin square theta. Okay, sigma t is equal to tau xy cos 2 theta. I'll call this as 4. Okay, now we got the expression for sigma n and sigma t. Therefore, if the body is subjected to pure shear, the normal stress acting on this plane PE is sigma is equal to tau x by sin 2 theta. The tangential stress or the shear stress acting on the plane is sigma t is equal to tau x into sin 2 theta. Okay, we need to find the principal stress on principal planes, maximum shear stress, and maximum shear planes. Okay, I will first talk about the principal stress tau x by sin theta. Just by from 3 sigma n, which is equal to tau xy sin 2 theta. The maximum value of sigma n can be sigma n reaches a maximum value 1 2 theta when 2 theta is equal to 90 degree. Isn't it? 2 theta is equal to 90 degrees, sin will become 1. Okay, 2 theta is equal to 90. If I write theta p or theta p1, which is equal to 45 degree, theta p2, which is equal to theta p1 plus 90 degree, or theta p2, which is equal to 135 degree. Okay, if this is the planes on which this normal stresses are maximum. If I substitute, okay, to find the planes of maximum principal stress. Now to find the magnitude of maximum principal stress, let us substitute theta p1 and theta p2 in sigma n. For theta p1 is equal to 45 degree, therefore sigma n is equal to tau xy. Okay, next sigma n, or you can call this is sigma 1 principal stress. Sigma 1 is equal to tau xy. For theta p2, which is equal to, for theta p2, which is equal to 135 degree, comma, sigma n, which is equal to tau xy sin 135 into sin 270. What is sin 270? Minus, right? ASTC, tan is positive, cosine is positive. This is sigma n is minus 2, which you can also write it as sigma 2 is equal to minus 2, minus 2. So if we represent in terms of planes, if we represent, these are the magnitudes, sigma 1 and sigma 2, there is the minus plus tau xy and minus tau xy. If we represent this, x, y, xy, theta p1 is at an angle 45 degree. We represent it. It is at an angle for a body subjected to pure shear. If a point is under pure shear, the principal stress theta p1, you should indicate like this. This is p1 plane, which is at an angle 45 degree from the x-axis. 45 degree is equal to theta p1. Perpendicular to it will be theta p2. Perpendicular, so that will be plane p2. Indicate it's a box. There's a plane. Magnitude of sigma on plane p1, sigma 1 is equal to tau xy. Sigma is equal to tau xy, it's positive tau xy. We can indicate it with positive tau xy, sigma 1, which is equal to, positive tau xy, sigma 2 minus tau xy, you can indicate it with compressive minus 2. Since this is principal stress, there is only principal stresses. In the magnitude of principal stresses, tau xy and minus tau xy. That's it. But it's tension and compression. It indicates tension and compression. This is sigma 2. Sigma 2 is equal to minus tau xy. This is sigma 2, which is equal to minus tau xy. Okay. Give me a moment. Okay. Have you understood this? Right? I'll go ahead for the shear stress plane. Maximum shear stress. We need to find the planes of maximum shear stress. To find the planes of maximum shear stress, sigma t is given by, which is equal to tau xy into cos 2 theta. Sigma t will be maximum for 2 theta is equal to 0 or 2 theta s, or theta s1 is equal to 0, 0 by 2 is 0, or theta s2 which is equal to theta s1 plus 90. Therefore theta s2 is equal to 90 degree. Okay. Now to find the magnitude of maximum shear stress, let us substitute theta s1 and theta s2. Okay. I'll substitute for theta s1, which is equal to 0, sigma t, which is equal to cos 0 is 1. Okay. Sigma t is equal to tau xy. Since tau xy is positive, left with 10 minutes, I'll try to complete. Since tau xy is positive, it will rotate s1 phase in counterclockwise direction. It will rotate s1 phase in counterclockwise direction. Okay. Next, for theta s2 is equal to 90 degree, sigma 2 cos 180 is minus 1 minus tau xy. It is nothing but tau max on the planes of maximum shear stress. These are the planes on which maximum shear stress occurs. If I substitute, I will get tau max and tau min. Tau min is equal to this. I need to find average stress also. To find the average stress acting on planes of maximum shear stress. Let us substitute in sigma n. Sigma n is given by sigma n is equal to tau xy into sine 2 theta. Okay. Let us see whether there is average stress or not. For for theta s1 is equal to 0, comma, sorry, sigma n which is equal to 0, for theta s2 is equal to 90 degree, sigma 180 degree, sin 180 degree is also 0, sigma n is equal to 0. So when I talk about pure shear stress, the planes are not accompanied with normal stress. The planes are not accompanied, since the pure shear, these planes are not accompanied with a normal stresses, that you should remember. If I represent in terms of the sketch, the normal axis, this is the xy plane, this is the plane where the shear stresses are induced, x and y plane. In from this plane, if I rotate at what angle, I will get the maximum shear stress or the maximum principal stress. I'm indicating here. I'm indicating the maximum shear stress, xy plane. Okay, theta s1 is at an angle of 0 degree. So theta s1, I will indicate this itself as plane s1, plane s1. Theta s2 will be obviously 90 degree to it. Theta s2 will be 90 degree. Theta s2 is 90 degree. You can indicate s1 plane. This as s2 plane. As soon as you write s1 plane, write the plane which indicates for this plane s1 is the normal. Okay, there's no average stress. Okay, since it is rotating the s1 place in the counterclockwise direction, since it's positive, I want to write this in counterclockwise direction. Since tau xy is positive, it will rotate s1 place in counterclockwise direction. I want to represent this in counterclockwise direction. This is like this, this is like this. This will rotate in counterclockwise direction. These two arrows will meet like this. These two arrows will meet like this. Its magnitude is tau xy. Okay, this is your shear stress, maximum shear stress representation. Okay, theta is equal to 0, and there is no average stresses. Okay, there is only shear stresses induced on this plane, maximum and minimum shear stress planes. Okay. A moment. Okay, that's all. Next, in the next class, I will talk about some simple derivation, some like sum of the two normal stresses is constant for a given state of stress. We'll discuss like that. Okay, and then that your plane stress condition, the derivation on 8 pages. I will not derive it, but I have derived already in my sheets. I will show it to you. I'll scan it. I'll make it as PPT, and we will discuss it. Derivation itself will take 3 or 4 classes for me, but I have derived it. I will explain as a PPT, and I will show you the notes of that. Same thing, but instead of what happens is, see, instead here we add only shear stresses, but also this will be accompanied with sigma x, sigma y. There will be three forces to resolve, and then this equation become little difficult. And also that sigma n and sigma t, since there is this now the equation becomes a little complicated, I cannot just say by inspection that when theta is equal to 2 theta is equal to 90 degree, my this expression becomes maximum. I have to derive it, I have to differentiate, I have to take it. It's a little complex it will become, but that is very important. Your entire problems revolves on the plane stress condition only. Okay, we will discuss this in the next class. I'll stop at this point. Any doubts you can ask me. Okay, shall I stop at this point? Shall I stop at this point?
Yes, sir.
Okay,
Yes, sir.
thank you.
Yes, sir.